Hello there, and welcome to this collection of notebooks and tutorials on multi-rate signal processing. This is a course offered by Professor Schuller at the UMNL University of Technology. I am Renato, and this notebook is about frequency response. We are going to revise and see ways of computing the frequency response, the relation between impulse response and frequency response. We will see how to calculate frequency response, and we go through many examples, a bit of revision on decibels, on filters. We're going to see the discrete convolution as matrix multiplication. Let's get started. The impulse response and the frequency response are related by the DTFT. This gives us two ways to describe a system, or in time or space domain with the impulse response, or in frequency domain with the frequency response, and we can go back and forth by taking the Fourier transform or the inverse Fourier transform. An impulse has a flat spectrum, and this allows us to investigate all the frequencies of interest in the frequency domain. But in many applications, it's not possible to feed a system with the impulse. This may damage or destroy the system, for example. And we can use different techniques to have a measurement of the frequency response. And from the frequency response, if we take the inverse Fourier transform, we get the impulse response. So we're going to take a look at two examples on how to measure a frequency response. First, using a white noise, because the white noise has approximately a flat spectrum, similar to an impulse. And then we're going to use a sweeping sinusoid, where we increase the frequency of a sinusoid and we keep the amplitude constant to get the measurement of the frequency response.
In this example, we are going to use noise to obtain the frequency response of a black box system. By black box system, I mean a system that we don't have any information about, that we don't know what it does. The only thing we know, we can pretend is just a black box that we can feed in some input signal and we can measure the output of this black box. The idea here is to use noise because it has approximately flat frequency spectrum, so all the frequencies we are interested to investigate are present in this input signal, and we will make use of the concept of transfer function. So in the frequency domain, we will divide the output of this black box by the input signal. This gives us a transfer function, and when we take the inverse Fourier transform of this transfer function, we will end up with an impulse response of the system. Here we are loading some Python libraries, so we are going to use SciPy to calculate the FFTs. We are going to use matplotlib and plotly to plot, and these are the signal processing parameters we are going to use for this example. So we're using a sampling frequency of 32 kilohertz and a number of FFT points, 2 to the power of 16 points. So that's approximately 65,500 and something. So the time interval we're going to use to generate our signals will be approximately 2 seconds. So we are using 32 kilohertz sampling frequency and 2 to the power of 16 points. That gives us approximately 2 seconds. Here is our black box system. So it's this array of numbers. So we can pretend that we don't know what's inside here. It's just a black box. But in any case, this is we can see as an impulse response of a system. And even if we look at those numbers, we don't know what it's doing. We don't know the characteristics of the system. So we will try to, when we get the frequency response of the system and we get the impulse response, we should get the same numbers as that are inside here, this black box. At this point, we're defining our input signal, so we are creating this noise vector from a normal distribution with zero mean and unit variance using 2 to the power 16 points. So this will give us around 2 seconds when we use a sampling frequency of 32 kilohertz. Here we are taking the FFT of this noise vector. So by default, SciPy using the length of this this vector we give it as an input to calculate the FFT. So this will be also 2 to the power of 16 FFT points. And here is our noise in the time domain. So we can, it's around 2 seconds, we can listen. So it sounds like noise. Here is our output signal, so we're convolving noise with the black box, and this gives us an output. So here we can listen to this output. So we perceive that there is an impression of much less high frequencies in this signal. This indicates perhaps an idea that our black box could be a low-pass filter. Here we are taking the FFT of the output of the black box, so it's the convolution of noise with the black box. Then what we will do is, like in the frequency domain, we are dividing the output of the black box by the input of the black box, and we have this shape here that really indicates like a low-pass filter. We are using noise, and we are using this technique of transfer function. This curve is very noisy, so what we can do is we can smooth out a bit this curve. So I will implement a moving average filter. So this is what I'm doing here. I'm creating a moving average filter with 32 points. And this red curve now is a smooth version of our transfer function of the black box. So just reminding, we divided the output of the black box with the input of the black box in the frequency domain, and this is what we are looking here. So the red is a smooth version, so I applied a moving average filter with 32 points, and we can see around 200 Hertz we have this minus 3 dB. So we could say that maybe this is a low-pass filter with a cutoff frequency of 200 Hertz. Then at 2000 Hertz we have minus 20 something dBs, and this indicate that there's a roll-off of minus 20 dB per decade, and this could be a characteristic of a first-order low-pass filter. So just by looking at this, let's say the frequency response obtained using noise in the transfer function of this black box, we already can see that this could be a low-pass filter. So then what we can do now is like if we take the inverse Fourier transform of the transfer function we just have here. This is what we do here, and we will plot those array of numbers that was our black box, and we will plot the inverse Fourier transform of the transfer function, and we can see that our calculated impulse response is very similar to the black box itself. So we succeeded in a good approximation. So this is what we expected. So after this process of measuring a frequency response and taking the inverse Fourier transform to end up with the same numbers that were inside this black box array. So by analyzing here, we've seen that it could be a first order low pass filter. And if we compare with a Butterworth filter, first order 200 Hertz cutoff frequency, we see that our black box is a very good approximation of this Butterworth filter. So in fact, what I did to have this black box is that I already had this Butterworth filter. Then I simulated some kind of impulse response using 128 points. So let's say it's a truncated version of impulse response of a Butterworth filter, as analog filters have infinite impulse response, but we can have approximation by truncating. So this is what I used to construct this black box. We can see that using noise and using this transfer function technique, getting the frequency response turned out to be a good approximation of a real system. In the second example, we are going to use the same technique, but instead of using noise, we are going to use a sweeping sinusoid as an input signal. And we also have a different black box, so we will call it black box 2, the same array of numbers, but let's pretend we don't know what's inside. Even if we look at these numbers, it's not saying anything to us. So our input signal will be a sweeping sinusoid. So here is where I am creating the sweeping sinusoid. It will go from 0 to 16 kilohertz. So it's the sampling frequency divided by 2, and we will have 2 to the power of 16 points. So here is how it looks like, just the beginning of our sweeping sinusoid. I'm not plotting all the points, otherwise it's difficult to see. And we can have the spectrogram of this sweeping sinusoid, and we see it goes to a bit more than 2 seconds, and frequency, we increase the frequency and we keep the amplitude constant. So we have here frequency from 0 to 16 kilohertz. So we can also listen to this sweeping sinusoid. What we do, the same procedure like before. We will take the Fourier transform of our input signal, which is the sweeping sinusoid, and here we can see the frequency domain, the frequency and the magnitude of our sweeping sinusoid. We can see that there is these parts with many oscillations, and this could be due to the Gibbs phenomenon, or we have these discontinuities in the beginning and the end of our signal. We're going to use the transfer function concept again, so it doesn't really matter that we have these oscillations here at this part, but just to revise a bit and for learning purposes, let's apply a window to our signal and see what happens in the frequency domain. So I will apply a Tucky window. So this is our sweeping sinusoid in blue, just the beginning of the Tucky window here in orange, and in green is the result of our signal. Our sweeping sinusoid in blue, just the beginning of the Tucky window here in orange, and in green is the result of our signal. We see that we're smoothing also the beginning and end of our signal, avoiding this kind of abrupt discontinuations. And then in the we can listen to the window. We don't really notice so much difference, but we can see in the frequency domain. So in blue was our original signal, and in orange is the windowed signal. So we can see that by introducing this windowing, we avoided this kind of oscillations. So it's normalized to the peak. So I'm normalizing here both signals. So this is why 0 to B is showing here. But we just see now that the windowed version of our signal get much smoother frequency characteristics. and we see that our signal has frequencies from 0 to 16 kilohertz. So this is what we want to investigate. And now we will convolve our input signal with the black box number 2. Then we will take the FFT of the output of the black box number 2, and we can also listen. We can notice that it seems to have less low frequency content when we take the transfer function. So we're dividing the output of the black box with the input of the black box, and we see that this is the curve that we obtain when we plot this transfer function. By analyzing here, we see these ripples in the pass band. It looks like a high pass, so it's cutting until around 8 kilohertz. It has these ripples, and it's at 800 hertz. It's already on minus 80, minus 78. We see here there is a roll-off that is more than 60 dB, but less than 80 dB. Perhaps this would indicate that it's a third order filter. And if you remember analog filters, the Chebyshev filter has these characteristics of ripples in the pass band and a steeper roll-off in the cut region that's more than the Butterworth filter. And if we compare with a Chebyshev filter type 1, so I'm constructing here a Chebyshev with third order with 3 dB in the allowance in the pass band as a ripple, 8 kilohertz cutoff frequency, and I'm also comparing with the Butterworth filter just so we can have an idea. So we see that the black box and the Chebyshev third order type 1 filter, they are very close to each other, so it could be a very good approximation. So we have much more attenuation in the Chebyshev, even if the same order as the Butterworth filter. If we take the inverse Fourier transform of our black box, we will have our impulse response of the filter, and again I expect it to be a truncated version of the impulse response of a Chebyshev filter. I also constructed this black box this way, so when we plot the impulse response and the black box, we see that they match. So indeed we have achieved our purpose of identifying the system using frequency response calculated using a sinusoid, sweeping sinusoid. So it's the same technique we used before, but with a different input signal. If you're interested in these techniques, I leave here a video that I took part in the MATLAB context 5 years ago. So I implemented a dual channel FFT audio analyzer. So it's based in this principle of transfer function, and I give a small demonstration in this video. And these techniques, they are used in many professional audio analyzers. So we have from Meyer Sound, the SIM3 audio analyzer. They use it to align sound systems. We have Smart, and we have many others, other manufacturers that are offering this kind of transfer function audio analyzers. So we can also obtain the frequency response of a system if we have the Z transform, if we replace Z by e to the power of j omega. So this is also the relation between z transform and the DTFT that we've seen before. In this case, when we replace z by e to the power of j omega, the formulas of both transforms becomes identical. And this is something like reading now the z transform along the unit circle in the complex domain. So we also have a periodicity of 2 pi, and we have that for real valued signals, there is a symmetry between the upper half of this circle and the lower half of this circle. So we have a complex conjugate symmetry in this complex plane. So by replacing z by e to the power of j omega, we can compute the frequency response of our system, and we can have an example of this process. So here we have a low-pass filter as a moving average. So this is the equation for this moving average filter, and we know that a unit impulse is equal to 1 when n is equal to 0 and 0 elsewhere. So if we replace here the unit impulse, x will be the unit impulse, and then we will have our impulse response h of n, and it will be half and half. So we can see the impulse response also in a vector way. So it's good to point out that the discrete convolution operation can also be written as a matrix multiplication when we use a so-called Sylvester matrix. So if we change the shape of our impulse response vector in the format of a Sylvester matrix like this, and then we have convolution in terms of matrix multiplication. So we have our input vector, we multiply by the Sylvester matrix, and we have an output, which is the discrete convolution. We can also change the shape of our input signal and multiply a matrix multiplication with the impulse response vector, and we still have the convolution. So we can have an example. I will use the impulse response the same as we have here, 0.5 and 0.5. And our test signal will be 1, 2, 3, 4, 5, sequence of numbers from 1 to 6. Here I'm creating the Sylvester matrix. So we have from our vector of impulse response, now we change it into matrix form using this so-called Sylvester matrix. And now if a matrix do a matrix multiplication with our test signal, which is a vector 1, 2, 3, 4, 5, 6, and we multiply by the Sylvester matrix, and then we will have our output. And in fact, we can see that when we use NumPy convolve, so the convolution by the NumPy library, and we have this matrix multiplication, we have exactly the same results. So another example, not using the Sylvester matrix, but using this change of shape in the input signal, we will now convolve our sweep sinusoid that we used in previous example with the black box number 2 that we also used in the previous example. So this is a high pass filter approximation of a Chebyshev type 1 of third order with 3 dB allowance ripple in the pass band, and the cutoff frequency was 8 kilohertz. So when we apply this matrix operation, so we're multiplying, we will change the shape of our sinusoid, sweeping sinusoid. So this is what we're doing here. And then we'll multiply with our black box vector. So it's the impulse response, and we will have our So if you remember the sweeping sinusoid, you've seen here that it removed the low frequencies from the sweeping sinusoid. And in fact, if we plot a spectrogram of the output of this convolution, we see that around it's cutting, attenuating the signals on the cut band, and then after the cutoff frequency, the signals are back to normal. So now we use here convolution as a matrix multiplication. So we can see the discrete convolution operation also as matrix multiplication. So let's go back to the frequency response. So the Z transform of this moving average low pass filter is given here. So when we replace Z by e to the power of j omega, we will have this thing here. And usually we're interested in a magnitude and phase of the frequency response. So we can take the magnitude operation here and the phase. So we can compute using Python. So here I'm importing SymPy, defining Z as a symbol. So we'll have Z transform as a polynomial. So this is what we're doing here. So we usually flip the coefficients of the impulse response, and then we construct a polynomial with Z to the power of -1. So here what we have is the Z transform. With a bit of expression manipulation we can change. So here it's easier to see that we have a pole when Z is equal to 0 and a 0 when Z is equal to -1, and we have also this gain factor of 0.5. And now if we replace Z by e to the power of j omega and we choose a desired frequency, so we're choosing 100 points between 0 and pi, so pi will be until half of the upper circle on the complex domain. So we're initializing a frequency response with complex zeros, and here we are replacing Z by e to the power of j omega. And then we can compute here, we have the magnitude response for 100 points. So we see that it's a low pass filter here. This is a normalized frequency, so pi is 3.14 here is the Nyquist frequency. And we see it's far from being a perfect ideal low pass filter. If we plot in the dB scale and also the phase, we will have here is what we're doing. We're plotting now in the dB scale, and we're also plotting the phase. So we see it's a linear phase with a slope of 0.5. So here we see the normalized frequency, so pi is the Nyquist frequency, and we see the slope of 0.5, so it's a linear phase. And here we can see the magnitude in the dB scale. We can also do using FreqZ, so I'm using the same 100 points that we used before. It will give us the frequency response and the omegas used to calculate, and we can plot. So here also is the magnitude in the dB scale. So this is our moving average low pass filter given by these coefficients 0.5 and 0.5. We can also make use of signal SciPy and Python control library to calculate magnitude and phase and plot zeros and poles and have different functions creating LTI systems. So here I'm extracting poles, zeros, and gain from the polynomial of the Z transform that we defined here. Here we can now plot the poles, zeros, and gain in this nice complex plane. So we have a pole when Z is equal to 0 and a 0 when Z is equal to -1. And we can create an LTI system using the SciPy signal libraries. That's what we're doing here. We can also convert from zeros, poles, and gain. And now we'll make use of the control library and have a transfer function. So from 0 poles and gain, we go to nominator and denominator of transfer function. Then we are using the control to have a transfer function, and then we can plot using this PZ map, and we have this kind of plot, which is pole zero map. So we have a pole when z is equal to 0, and a 0 when z is equal to -1. And we can also, with this transfer function system, we can use the Bode diagram, and we have our magnitude and our phase, just like we did with previous techniques. We come to the end of this notebook with a revision of the decibels. So we'll go through an experiment, and in this process we will investigate different characteristics of the decibels and many other things. So in this experiment we will have two input signals. So we'll have a sine wave with 50 Hertz and an amplitude equals to 2, and we will pretend this, for example, our voltage values, and we will have a cosine with 2 kilohertz and the amplitude of 10, and we will add these two signals. When we see we have our sine wave, so I'm plotting just the one period of the sine wave, and then we have our cosine with amplitude of 10 and our sine wave with amplitude of 2, and when we add these two signals, we have this input signal here. So then we will take the FFT of this input signal, and here I'm having the FFT, that now I'm using 2 to the power of 16 a number of FFT points. I'm calculating the magnitude, I'm compensating here for the number of FFT points and the frequencies on the negative frequencies. So when I plot the magnitude of the FFT, we have here our two components, one at 50 Hertz, another one at 2000 Hertz. So we have here a magnitude of almost 10. But here we already see that our magnitude is 1.5. So this is due to the scalloping error. So it happens, the FFT here has a limited number of FFT points, and depending where your frequency is located, maybe it's not in the center of the beam, but it's in the middle of two beams, and we have this error in amplitude. So bear in mind that when we don't have any window, we are in fact using rectangular window, and the rectangular window has certain characteristics in frequency. So what we can do is we can use windowing, and a very good window to estimate the amplitude of sine waves in the frequency domain is the so-called flat top window. So what I'm going to do here is I'm creating this flat top window, and then I am multiplying our signal in time domain with this window. Then I'm taking the FFT of the windowed input signal, and here I taking into consideration also the window, and now we have here our new windowed signal. So the magnitude and also in dB scale. So now the same signal, but a windowed version of this signal, and we see now we have 2 at 50 Hertz and 10 at 2000 Hertz, which were the original amplitudes of our input signal. And now we come in the dB scale. So we will take a reference as 1 voltage. So we had an amplitude of 2 volts. In the dB scale, it will represent by 6 dB. If we have 10 volts in the dB scale with a reference to 1 volt, we have 20 dB. So we can already see that there is a ratio of 2. So 2 volts and our reference voltage is 1. So we get 6 dB. And when we have 10 volts and the reference voltage is 1 volt, we have 20 dB. So let's go back and revise the dB. So dB is a ratio, and now we have two different equations depending if we're dealing with voltage or if we're dealing with power. So usually we can have power is proportional to the voltage squared, and this is why we have this difference. So the equation for voltage is 20 log 10 of V2 divided by V1, and SimPy already transforms this log 10 as two natural logarithm in the base of natural logarithm. So it gets 20 log of V2 or V1 divided by log 10. So this is what SimPy already simplifies the logarithms in the base 10 to 2 division in logarithms of natural logarithms. So, and we see the biggest difference here is that we have 10 log for power and 20 log for voltage. So if we have our values here and we solve these equations, we will see that, for example, when the amplitude is 2, and then our reference voltage is 1, our voltage is 2, and then we have 6 dB as we've seen here. So we had 2 here and we have 6 here. We will now design some filters and make more experiments with our input signal. So I will start designing a Butterworth filter, a low pass, second order, with a cutoff frequency at 200 Hz. And we can see here's the frequency response of the low pass filter. So I'm giving a gain of 10, and as we've seen, a gain of 10 in dB scale is 20 dB. Then I'm also designing a high pass Butterworth filter of first order with a cutoff frequency of 1000 Hz, or 1 kHz. So this filter has no gain, so it should be 0 dB in the log scale. So we have our high pass filter here, and now we will cascade these two filters, and we will see the resulting cascading filter is somehow a band pass, and we see that we had here 20 dB gain in the pass band of the low pass, but when it's cascaded with this roll off of minus 20 dB of the high pass, then we will have here the resulting attenuation in this frequency region. So we see that here we have at 200 Hz. So if we zoom in 200 Hz, we have 2.81 dB. This is the result, because we have 16.9 dB here from the low pass, and we also have approximately, so it's minus 14. So we add these two dB and we have the resulting dB here. So on when we see our input signals, so we will see we have here 6 dB, but our filter will attenuate at 200 Hz. We will attenuate at 50 Hz. We will attenuate minus 6.03 dB, and at 2 kilohertz, it will, our resulting filter will attenuate minus 21.175 dBs. So this what we will do now is we will take the we'll filter our signals in the frequency domain. So we are multiplying our input signals by the cascaded filters. And then we will already solve our dB equation for V2. And so now we will compare the signals before filtering and after filtering. So our reference voltage now would be before filtering. And we want to find out what will be the new voltage amplitude with filtering. So we solve for V2 and we get this equation. And when we substitute the value, so our voltage was 2, and then we will have a attenuation of minus 6.025 dB. So the new amplitude for the 50 Hertz component should be 0.99, so approximately 1. It makes sense because minus 6 dB is like if we're a ratio of half, so 0.5, so 2 divided by 2 is 1. 2 divided by 2 is 1. And for our frequency component of 2 kilohertz, it was 10 volts before filtering, but we'll have an attenuation of minus 21.175, so it's a bit more than 20 dB. If it would be 20 dB, then it will be 1 volt. So we have this ratio of 10, gain of 10 and 20 dB in the dB scale. So the new amplitude for the 2 kilohertz component will be 0.87. So if we if we plot the frequency domain, in the frequency domain, our output signal, we will see that indeed we have an amplitude of approximately 0 dB in the 50 Hertz component, that it's equal to an amplitude of 1, approximately 1, like we calculated before, and the 2 kilohertz component is minus 1.17 dB, and it's equal to 0.873, like we calculated with the equations for dB. So we've seen that when we cascade two systems, and then in dB we're going to add the attenuations or gains, and we see there's a ratio of 6 dB in voltage. That is, we're doubling the amplitude, and if we have a 10 times ratio, we have this 20 dB, and we see also that 0 dB gain. It's in the dB in the amplitude is equal to 1, so there's no change, there's no gain or no attenuation when it's 0 dB. And this was our revision of decibels, and it's the end of this notebook about frequency response.